Hi, I'm Stefan Lemmer, and I will be presenting the work Crowdsourcing More Effective Initializations for Single Target Trackers Through Automatic Requerying, which I have done in collaboration with my co-authors Jean Song and Jason Corso. Single target video object tracking is a canonical task in computer vision. The task consists of 3 steps. First, the user provides a video. Next, a bounding box is drawn around a semantically meaningful object in the first frame of that video. Last, a model tracks the object given in the first frame through the remaining frames. From the perspective of this work, the last 2 steps each encode an important assumption. In the second step, we assume the first frame bounding box accurately describes the target in the input space. And in the third, while some evaluation methods do consider robustness to perturbation, it is generally assumed that equally good bounding boxes result in equally good object tracks. We examine these 2 assumptions and their implications under a crowdsourcing framework. Broadly, this work asks 3 major questions. Are the assumptions of video object tracking valid when used with crowdsourced data? Is the typical crowdsourcing goal of optimizing in the input space valid with respect to inference in video object tracking? And, if these assumptions aren't valid, how do we address these inconsistencies in a way that balances the number of queries, actual performance, and optimal performance? We begin by examining the assumption that the received bounding box accurately describes the target in the input space. Using data collected across 900 crowdsourced initializations on the OTB100 dataset, we see that 8.9% of initializations have an intersection over union greater than 0.9 with the gold standard, 55.4% are between 0.7 and 0.9, and 93.1% are greater than 0.5. This means that many, but not all, initializations could be considered high quality in the input space. More important, however, is the effect of these received initializations on the final object tracks. This is partially addressed in the assumption that equally good bounding boxes result in equally good object tracks. We see in the 2 displayed object tracks that for the same video, a slight change in initialization can result in substantially different performance. This is reinforced by an aggregate analysis, which shows that additional error, the increase in error when a non-gold standard seed is used, typically decreases as the initialization approaches the gold standard, but the correlation is not definitive. Good initializations often result in poor performance, and poor initializations often recover and perform as well as the gold standard. These findings affect how current crowdsourcing strategies, typically based on some sort of consensus in the input space, would work on this inference problem. Through this analysis, we find 2 major shortcomings. First, such strategies would require multiple queries on all initializations, even the 23.3% for which the crowdsourced initialization performs as well as the gold standard. Second, such methods optimize the wrong objective, as the goal is to optimize performance in the output space, and the correlation between input space and output space quality is not definitive. To address these shortcomings, we introduce smart replacement, which consists of a requery function that determines whether or not to accept the first initialization, and a selection function that, after receiving the second initialization, determines which initialization to use for the final inference. Under this paradigm, we aim to requery only if necessary, minimizing the total number of queries, and, if a second initialization is provided, optimize output performance by choosing between the 2. The performance of our smart replacement method is compared to previous methods using a novel metric called the replacement mean additional error, or RMA, which finds the mean additional error across all chosen initializations. The relationship between RMA and the proportion of initializations accepted without requery, coverage, is shown for both previous and our methods in these figures, and summarized as the area under the curve in the tables. We see that not only does smart replacement improve the overall performance of the model when compared to naively accepting the replacement initialization, but also changes which scoring function should be used for both requery and selection. To summarize, we have shown that the assumptions used in evaluation of object tracking algorithms, namely that the initialization will be good and that equally good initializations result in equally good outputs, are too simplistic with respect to a crowdsourced scenario, and that current crowdsourcing methods that focus on aggregating multiple inputs to find the optimal answer in the input space will both requery many unnecessary initializations and optimize the wrong objective. We then evaluated potential methods for detecting and correcting bad initializations under our smart replacement paradigm and showed the importance of this method, which not only improved overall performance, but changed the requery and selection functions that should be used.